Okay, my friends, now we're on. So yeah, if we can just go ahead and get through this thing. I am recording this for the folks that were taking the PSAT, and I am asked to give a shout out to Jeffrey Lynn! Yeah! This is where we ended yesterday. We were talking about how to figure out what the oxidation number of elements were. Each element in a chemical equation we'll have to find the oxidation number for. So we had done these, very simple. I'm going to just begin by going over a couple others that we didn't do. What would be the oxidation numbers of the N and the O? Yeah?
Oh, the N would be +5 and O would be -2.
And how would we get that? We know the O is -2 because it's almost always -2. What about the N?
There's a charge of -1. So like, since it's like -2 times 2 is -6, we need to get to -1 would be +5.
Yeah. O is contribute to -6. So what does N have to be so that when you add it to -6, you get a -1? That's how we think through those polyatomics. How'd you do that so fast? Okay, good. Did Lynn tell you how to do it?
Wait, what?
Wait, what? What about this one? CO.
0.
Yeah, that's an element. That's just, that's cobalt. No charge. That would have an oxidation number of 0 on its own. Okay, I saved the best for last. What would be those 3 oxidation numbers?
Can we start with oxygen?
Yes. Should we start with oxygen? Yes.
Ooh, so
So you know the oxygen is -2. I think you know the potassium as well.
+1.
You look up there at the periodic table. Oh yeah, loses 1 electron, positive 1. I know there's 2 of them, but you would say that the oxidation number of potassium is +1. So do the math. What does the chromium then have to be? +6. Yeah, because you got +2, -14, so that adds up to +12. And then there's 2 chromiums, so each one has to be a +6. All right, so that's what we do to find oxidation number. The next thing that we'll have to do with redox is we'll have to be able to balance redox equations. Redox equations sometimes can be impossible to balance the way that we've learned. The way that we've learned how to balance, when you look and you inspect one side, you see how many atoms are of this element are on this side. Make sure that the same number of elements are on that side, same number of atoms of each element on the other side. And then you go through that for each element. We call that balancing by inspection. I call it that because the Zundals call it that. If you look at, this will be, well, I'll do this one tomorrow. This will be how we calculate or balance these equations. Take a look at this chemical equation. This is not balanced. You don't have to write this down. We'll do this after we go back one slide, but I just want you to see this. This would be a redox reaction. We'll see why in a moment. The way that we've learned to balance before, you would expect, okay, I have 2 BRs over there. Well, I need 2 here, so put a 2 there. 1 Mn on the left, 1 Mn on the right. 4 O's on the left.
Uh-oh.
The oxygen doesn't even show up over there. How can that be? Well, it can be. That's the way some redox reactions are going to look. So we're going to have to do something different to balance this thing. You just put 4 O's over there? No. So that's where this slide is going to be useful to us. We balance redox equations. John, would you mind closing the door for me, please? We're going to balance redox equations if you can't balance them by inspection. If you can balance them by inspection, then do that because it'll save you time. But if you can't balance them by inspection, then you want to do what we call the half reaction method. Some of us do this in Chem 1, and some of the Chem 1 teachers don't do it. So maybe all of us did it last year. Does everybody remember seeing the half reaction method? Siddharth.
We did.
Sorry.
Yeah.
How do I
Go away.
I don't think
We
we
start this week, okay?
Wait, I don't
We
think
probably did
redox.
it, but
Okay.
I forgot it, so I'd like a little review.
All right. Yep. So if you did it last year, this is going to just start coming back to you. And if you didn't do it, it's not terrible. It's going to look intimidating because there's a lot of words. But it turns out you'll do a couple of them, and then it's very systematic, which I like real well, because you want you're doing the same thing every time. To me, balancing redox equations with half reaction method is like a puzzle. It's like you're doing a puzzle for it. I don't know. To me, it's fun to do redox balancing. I've always enjoyed it. I can do them all day and enjoy that. It's a little nerdy of me to say, but I do. I like it.
Yeah.
We do need to know whether the reaction's occurring in an acid or if it's in a base. The first scenario is going to be assuming that the reaction occurs in an acid. If you haven't seen this before, what you write on this slide is not going to make any sense. You're going to be saying, I don't know what he's trying to tell us to do. But just write it down. And then when we do the example, you'll see that I'll go through every step. And when you see it being done, it'll make very good sense, I hope. So number one, write separate half reaction. What does a half reaction look like? Well, I'll show you. Number two, balance all the elements the way that we always do it, except for the hydrogen and oxygen. They're going to be different. So we have two half reactions. We just start to balance them, except for H and O. And once you get to the H's and O's, we're going to do the O's first. When you have O's, and you saw that in the example that I gave, we have O's on one side of the equation, but not on the other side. If you need to add oxygens, you're going to add them in the form of water molecules. Oxygen atoms and ions do not float around very easily on their own. They're very reactive, and they tend to grab onto things. So because this thing is an acid, the oxygens that are free are going to take hydrogen ions and bond to them and make water. So however many O's you need on one side, you add that many water molecules. Now for the hydrogens, because this is in an acid, you're going to use hydrogen ions to balance the hydrogens. Does this come back to you at all, sir? It still doesn't. Nisha, if you didn't have your notes, would you remember doing this?
No.
Wow.
Well, I remember doing it, so I wouldn't know how to do
Yeah.
it.
Yeah, well, that's not what I mean. I wouldn't expect you to remember how to do it. Anna, do you remember?
Yeah.
Do you? And then who else from last year? David, do you remember how to do these? Annie, do you remember doing this last year in Chem 1? Don't you? Not at all? Oh my gosh. That's funny.
I had 30.
You guys did it in Barrett's class, I know.
Yeah.
Yeah. Okay, so number 5, once you have, now by the time you've done 2, 3, and 4, you've got both half reactions balanced in their atoms. You also, though, step number 5, we have to balance the charges. You need to make sure that the charges are the same on both sides of each half. So we'll use electrons for that. So with all redox reactions, you're going to have to do this step number 5. Remember, the redox is all about transferring electrons. There's going to be something that loses electrons, and then there's going to be something else that gains electrons. So in these two half reactions, one's going to be the oxidation. Remember what the definition of oxidation is. It's the loss of electrons. So that's why I say that there are always products in the oxidation half, and then reduction is the gain of electrons. There will always be reactants in the reduction half. Number 6, once you, it's not just enough to get the electrons in there. The electrons have to be the same number in the oxidation and the reduction. If you give off 5 electrons in the oxidation, you need to take in 5 in the reduction. You can't have extra electrons or a deficiency of electrons. You've got to have the same number. Okay, and so once you've done this step, you've got the number of electrons equal. Now at this point, we have 2 half reactions. We add them back together to get one overall equation. And if there are any spectator ions you had left out, then you put them back in at the end. So with that, we'll go to an example. This example that I gave you, I'm going to get rid of this 2. That's not going to stay. And before we do anything, let's just even see if this is a redox reaction. Now, the fact that we can't balance it conventionally is a pretty good indication that it's a redox reaction. But let's look at this thing and identify who gets oxidized and who gets reduced. We do that by figuring out the oxidation number of every single term in the equation. So Br with the -1, what's its oxidation number? -1.
Wait, dude.
MnO4 negative, the permanganate ion. We know the O is -2. What's the Mn? +7. That's right. Got a -8 here. What plus -8 equals -1? It would be +7. +7 is a very high oxidation number. So this is a pretty reactive ion. The permanganate ion is involved in a lot of redox reactions. That always is going to reduce. And then Br2, what's the oxidation number of the Br in Br2?
0.
Yep, it's an element by itself, so it's 0. Over here, it was a charged ion there. It's negative, so that's why it wasn't 0 there. And then same thing here. Mn +2 has whatever its charge is as its oxidation number. Okay, so it looks like the bromine, the bromide ion, is -1, and then it changes to 0. Its oxidation number goes up. That means it was oxidized. Increase in the oxidation number is oxidized. Decrease is reduced, and there is our manganese, +7, going down to +2. That gets reduced. The way that we write our half reactions, and I'm going to model it the way that I'd like to see you do it. Over on the left side of your paper, give yourself an ox and a red. Now it comes back, right? Yeah. Give yourself some room. Don't write anything right next to the ox and red. Go over here to the center of the page and write down for the oxidation, just write down what you started with and what it oxidizes to. It was Br negative, and you're going to do the thing that oxidizes over here. The thing that reduces is